Hello students, my name is Shashank Shekhar. So today we will start the chapter Biomolecules. So if you look at the syllabus here, so we have five main parts of this chapter, starting from carbohydrates, proteins, to enzymes and hormones. I would say they are in the same category. Then we'll talk about vitamins and nucleic acid. Now today we will start from carbohydrates. Before that, we will see a general introduction of that, of what biomolecules are basically. So, if you look at a body, I would not say at the macroscopic level, but at the microscopic level, then you will find that they are composed mainly of carbons. Means most of the composition is attributed by the carbon, and I would say long chain of carbons. So, all the molecules that are just constituting our body and the body of every living being is called as biomolecule. Now, if I see the today's topic, so we'll start from the first type of biomolecule, that is carbohydrate. Then we will look at the classification of carbohydrate on different bases. Then reducing and non-reducing sugar, it is also a classification which is based on the nature of carbohydrate, whether it reduces or not reduces a given reagent. Further, we have monosaccharides. So let us start our today's topic from the carbohydrate part. So if you try to define carbohydrates, so carbohydrates are generally the hydrates of carbon, and it is the way the name is derived. Means basically, if you see the formula, so it is having the formula of CzH2O whole Y. So you can see here that the carbon is being hydrated in some way by addition of H2O. So it is a hydrate of carbon. For that reason, its name was kept as carbohydrate, but later on this concept was demolished due to some exceptions, and now we do not define it in this way. Okay, so carbohydrate on hydrolysis produce polyhydroxyaldehyde and polyhydroxyketone. So what is the meaning of this? So if you try to hydrolyze carbohydrate, then you will get polyhydroxyaldehyde. So polyhydroxyaldehyde means aldehyde that contains multiple number of hydroxy group, that is OH group. Okay, similarly we will have several units of polyhydroxy ketone. So basically we will have ketone, that is C double bond O. Along with that we will have OH bond that is present in the structure. Now the number can vary depending upon the structure of the carbohydrate that we have hydrolyzed. So if you talk about the examples or the source of the carbohydrates, so we can have cane sugar, glucose, starch, and other example like your daily sugar which we use. So most of the sweet things that you taste in your daily life are generally carbohydrates containing. Okay, so they generally contain carbohydrates. Next, now if you want to now define the carbohydrate, so they can be defined as active polyhydroxy ketones or aldehydes. So optically active polyhydroxy ketone and aldehyde means they will show optical activity, means they will show RS nomenclature, and upon the hydrolysis of this carbohydrate they produce such units of power of hydrolysis. So they will we have seen what is the hydrolysis product of carbohydrate. So it is polyhydroxyaldehyde and ketone. Now if I look at the definition back here, so what is the definition of carbohydrate? So if you break down this definition, you will see that it is written that they are optically active polyhydroxy aldehyde or ketone, means they are aldehyde and ketone functional group. So aldehyde functional group looks like this, and ketone looks like this. Now, as I have already defined, why I am saying polyhydroxy, because it will contain a number of hydroxy group. So suppose we can take an example like this. So it is our, say, ketone. Now we can have OH here, OH here. So you can see here that this is a ketone containing a number of hydroxy group, and it is also optically active as it has no element of symmetry present in it other than CN. See, it can have CN. We will not look into that. So if you want to just look at it, it does not have any plane of symmetry or either inversion center. So it is a carbohydrate. Now, if you do the hydrolysis, you will get several units of this several units of again polyhydroxyaldehyde or ketone. Okay, so you will get the same thing. Only the chain length will change. So we'll see how it is done and what is the hydrolysis product. So is this clear? So this is the basic introduction of carbohydrate. So we have started the definition that it is a hydrate of carbon. You can see it from the this general formula, but later this concept was demolished because some exceptions were found, and it was further defined as an optically active polyhydroxyaldehyde or ketone, which on hydrolysis gives the unit of again polyhydroxyaldehyde or ketone. Now the general examples, as I mentioned earlier, so the sugar you taste, the sugar you have in your home contains carbohydrates. Now that carbohydrates can vary, it can be glucose, sucrose, fructose, anything. In your milk also you have lactose, and then you can have this in your jaggery. So if you taste jaggery, it is sweet in taste, so it has also carbohydrate. So this was the definition of carbohydrate. Now next, let us look at the classification. So what is the classification? So we are trying to classify things because classification makes the study of carbohydrates easier, because there are a number of carbohydrates that are available in our environment. Now we need to study each of them. Now to study each of them individually would be very difficult. So we have tried to define it, or you can say classify it, on different bases. First is physical characteristics. So on the basis of physical characteristics, we have defined it into two forms. First is sugar, second is non-sugar. What is sugar? So if you look at this word, you can get an idea that it is sweet in nature. So carbohydrates which are sweet in nature are called sugars. Okay, so they fall under the classification of sugars, and those which are non-sweet, or you can say tasteless, they are termed as non-sugar carbohydrates. If you talk about the form, so it is crystalline in form, the sweet sugar. So if you want to just justify the statement, you can take a cube of sugar, put it under microscope, then you will see a long range order of the structure. Whereas other are amorphous, the non-sugar. So they are crystalline in nature, sugar are crystalline in nature, and non-sugar are amorphous in nature. Then if you try to dissolve this carbohydrate into water, then it will quickly dissolve. If you take sugar, you take the general sugar, the common sugar you use in your home, okay, and you dissolve it in water, then it will easily dissolve. Now let me make one thing clear here, that you say sugar for the household sugar, but sugar is not a name given to a specific type of compound, but it is a general characterization for all those carbohydrates which taste sweet and have these following characteristics. So you should not get confused. Okay. So it is readily soluble in water, whereas the non-sugars are not readily soluble in water. Now, due to the crystalline structure, they have a very sharp boiling point, whereas the non-sugar, which are amorphous in nature, have variable boiling points. So the examples are glucose, sucrose, fructose, lactose, and this one is starch. Non-sugar and starch. Now, when we will study more about the carbohydrates, you will see that this glucose, sucrose, and fructose, that are sugars, are generally mono or disaccharide. So we will know what is mono and disaccharide. So I'm just giving this piece of information before, because that it would help you later on. So when you will study monosaccharide, you will see that all these sugars which are sweet in nature are, say, monosaccharides, whereas when you will talk about the non-sugars, they are generally polysaccharides. Clear? So this is the direct distinction between your sugar and non-sugar. Now, what is the next basis on which we define it? It is on the basis of the hydrolysis product. So as I have told you earlier, so if you hydrolyze a, say, your carbohydrate, it gets hydrolyzed or say degraded into smaller components, and that are also polyhydroxyaldehyde or ketone. Now, if you are unaware about what is hydrolysis, so basically, if you react something with water, then you are doing the hydrolysis of that. Okay, hydrolysis means reaction with water. So reaction with water is hydrolysis. So based on that, so as I have mentioned the terminology, monosaccharide, disaccharides, and trisaccharide, they are the classification that is based upon this thing only. So as I have told you earlier, that we have seen that most of the sugars that are sweet in nature fall under the category of mono and disaccharides. You can see here fructose, glucose, galactose, lactose. So they all are almost sweet sugar, and they fall under the category of mono and disaccharide. Where the starch that we talked about in the non-sugar part is present in the polysaccharides. Clear? Next, let us see this classification. What is hydrolysis product? So if you are taking a carbohydrate and you are hydrolyzing it, and you are not getting any simpler units further, then we would say that that sugar is monosaccharide. Mono means single unit. Okay, it is a single unit of saccharide. So you are telling a unit of carbohydrate saccharide. So if you try to just hydrolyze this glucose, you will not get any further product, or it will not be decomposed into further any polyhydroxyaldehyde or ketone. Similar is the case for fructose and for galactose also. Now what is disaccharides? So if you hydrolyze something, some carbohydrate, and you are getting two products, two monosaccharide units, okay, so in that case you will call it as disaccharides. If I talk about the example, we will have sucrose. So you can see here, so if we hydrolyze this sucrose, then you will get glucose as well as fructose. Clear? Similarly, if you hydrolyze lactose, you will get glucose plus galactose. Next, if you hydrolyze maltose, you will get this glucose and glucose. So 2 moles of glucose you will get. Now, it is not necessarily important that you will get the same glucose here and here. This and this glucose can be different. So that would look absurd from the first saying, but believe me, when you will know more about glucose, you will see that several forms of glucose can exist. Okay, so the sucrose, the glucose that is present in sucrose may or may not be same to the glucose that is present in lactose or any other carbohydrate like maltose. Clear? So there are certain classification of the glucose. Further, we will see it on the basis of the structure. Okay. So what is disaccharide? So disaccharides are those carbohydrates which on hydrolysis give two monosaccharides unit. Similarly, that say carbohydrate which on hydrolysis give multiple monosaccharides unit, that is having length of, you can say, a counting of 10, 12, can go to 30, 40 depending upon the carbohydrate that we are dealing with. So they are very complex in nature. These carbohydrates are very complex in structure. They can have multiple branching. So these carbohydrates which produce several units on hydrolysis are called as several units of monosaccharide unit. I would say monosaccharide unit are called as polysaccharides. So generally, these polysaccharides that we're talking about are mainly found in plants. Okay, plants and animal tissues. Okay, they're found in plants and animal tissues. The examples are starch, glycogen, cellulose. So cellulose is generally found in plants. Glycogen is found in animals. Okay, so we'll see about them. Much more in more detail. When we will move to the specific topic, that is starch, glucose. We will also see the structure there. We will see the structure of each of this. We will talk about glucose, fructose, galactose. We will see the structure of each of this. That how this hydrolysis results in the final product. Next is the basis on the reactivity. So we have taken a reactivity, reactivity basis to classify it. So based on that, they can be reduced into reducing sugar and non-reducing sugar. What are the two types of sugar based on the reducing nature? Reducing and non-reducing sugar. So if it has a free aldehyde, okay, free aldehyde or a ketone group in Haworth projection, we see the presence of an OH group at one position. So what is this statement here? We will cover it later. So if you talk about a reducing sugar, so basically what are we doing? We are reacting our sugar with Benedict solution, filling solution, or Tolvin's reagent. So they all are aldehyde sensitive. So if you treat our sugar with this, say, filling solution or Tolvin solution, they will react with it if it has a free aldehyde. If it has no free aldehyde, then there should be an OH group present at the first position of the Haworth projection. What is Haworth projection? We will see it. Okay, when we will see the structure, open structure and closed structure and all those cyclic structure, you will see what is the presence of OH group at first position means to. So if you talk about the reducing sugar, we have the example of maltose, lactose, mellibiose, gentiobiose, cellibiose, menotriose, and rhamnotriose. So these are some example of reducing sugar. So what they can do, they can reduce Benedict solution, means they can be reduced by Benedict solution or failing solution. They can reduce, I would say, they would reduce Benedict solution, failing solution, and Tolvin's reagent. And itself they are getting oxidized. The CHO group will get oxidized to carboxylic group. So we'll see the reaction later on when we will study more about the structure and all. Okay. Now, if you talk about the non-reducing sugar, so non-reducing sugar are those which lack the free aldehyde or ketonic group. Okay. Or they do not have OH, they do not have either OH group, free OH group present at one position. So such sugars are called as non-reducing sugar because they cannot reduce Benedict solution, failing solution, and Tolvin's reagent. What is the example? The first common example that is often talked is sucrose. Then we have trehalose, raffinose, gentiose, and melagitose. So all of these examples are very complex. You do not need to remember all of this, but I would suggest that you should remember non-reducing sugar, at least that is sucrose, you should remember, and trehalose. Trehalose, I would not say raffinose. This two you should remember, and the remaining other are reducing sugar. Clear? So one more name you can add here. It is also a reducing sugar. So we have defined our carbohydrates on three bases. First, based on the taste or the physical characteristics. So if it is sweet in taste, then it is called as sugar. If it is not sweet in taste, then they are termed as non-sugar. We have also seen one general trend that normally your mono and disaccharides are sugars, and your polysaccharides, which are long chain of, say, monosaccharides units, are generally non-sugars. Sugars have a crystalline structure, whereas non-sugars have a amorphous structure. Sugars which are having crystalline structure have a sharp boiling point because of the fixed structure, whereas the non-sugars do not have a sharp boiling point. Clear? So what were the examples? The examples of sugars were glucose, fructose, lactose. Okay, and the examples of non-sugars were starch, cellulose. You will also take. Next, we have tried to classify it on the basis of say your hydrolysis product. Okay, on the basis of hydrolysis product. So on the basis of hydrolysis product, we have seen that if you are hydrolyzing a sugar and it is getting reduced to only 2 units, okay, if it is getting reduced to only 2 units, then it is called disaccharides, and if it is getting reduced to more than 2 units, then it will term it as polysaccharides, and if it is not getting reduced at all, then we will call it as monosaccharides because it has only 1 unit of monosaccharide. So disaccharide is something which is composed of 2 units of this, say, monosaccharide. Similarly, trisaccharide, we can also have trisaccharide, which will be a 3 unit of the monosaccharide, and polysaccharide which are multiple unit of the monosaccharide unit. The examples are, so if you talk about the disaccharide example, we have fructose, we have lactose. If you talk about the polysaccharide, we can have this, say we can have this starch, cellulose. Okay, so yeah, fructose is not a disaccharide, sorry for that. Fructose is a monosaccharide. Clear? At last we talk about this the classification. This classification is based on the reducing nature. So if your sugar is reducing in nature, if it is reducing your Benedict solution, filling solution, and Tolwyn's reagent, then we will call it as aldehyde. Sorry, reducing sugar. So what is the way that we can identify a reducing sugar? So at least it should have a free aldehyde group, that is the CHO group, and if it is not present, then it should have at least one OH group free present at the one position of the Haworth projection. You will see what is Haworth projection. And if none of these is present, then we will call it a non-reducing sugar. The example of reducing sugar are maltose, lactose, glucose, whereas the example of non-reducing sugar are sucrose and raffinose. Clear? Now next, we will talk more about reducing and non-reducing sugar. So if I talk about the reagent that we are that we have seen, the types of solution, that are Benedict solution, filling solution, Tolwyn's reagent, these are the 3 tests I talk about. So you must have studied this test in the aldehyde, ketone and carboxylic acid chapter. So what are these tests? So first of all, the Benedict's test. So in Benedict's test, we take copper sulfate, which is present in alkaline citrate. Okay, copper sulfate that is present in alkaline citrate. Then we have the filling solution, in which we have the copper sulfate in tartarate. What is the structure of tartarate? Right, just we have seen in this in carbohydrate. Try to remember it. It is very important that you remember the titrate structure. Okay, then we have the Tolwyn's filling solution, Tolwyn's reagent. What is the Tolwyn's reagent? So basically it is a test, it is a solution that is having silver nitrate in aqueous ammonia. Clear? So what are the reactions that are involved to it? What are the reactions that are involved to it? So in case of Benedict solution, we have the say our copper 2 plus, we have a copper 2 plus ion. So if we react our copper 2 plus ion with a reducing sugar, then this reducing sugar is oxidized to carboxylic acid. And what is the indication of that? We have the formation of Cu2O with the citrate ion. Okay, we have the formation of Cu2O with the citrate ion. Clear? So what is the structure of citrate? So citrate looks like this. So we have OH here, then we have O minus, then again we have one unit of carboxylic O minus, and we have again one more unit of this. So this is citrate. Clear? So we have a salt of citrate with copper as the other unit, or you can say as the counter ion part. Clear? So in this reaction, your Cu2 plus, that the copper 2 plus, is being reduced to Cu plus. And what is the indication? So we will get a brick red PPT. Clear? Next, what is the next one? Now what is the color of the non-reducing sugar? It is reduced to this deep blue color in both of these cases. Now if we talk about the citrate, so citrate looks like this, tartrate looks like this, copper sulfate in alkaline tartrate. So tartrate looks like this. We have O here, then we have OH here, one more OH here, one O here, and one O minus here. So this is tartarate. So copper sulfate in alkaline tartarate. So when we react this thing with our reducing sugar, then we again get brick red PPT as our reducing species is same here also. We have Cu2 plus getting reduced to Cu plus and the formation of Cu2O, and Cu2 is brown in color. Clear? Now, next is our Tolvin's reagent. So in Tolvin's reagent, we get silver color. Why? Because Ag is formed. So we have silver nitrate in aqueous ammonia. Then upon reaction of this silver nitrate in aqueous ammonia, we get a complex. Okay, we get a complex. What is this complex? So this complex looks like this. Okay, so complex looks like this. Before that, let me give you the failing solution formula. So these are the two ions that are present. This O minus and this O minus. So the first counterpart formed upon this is, so if you react with copper sulfate with alkaline tartrate, you will get O C H C O O minus K plus. Okay. Then we have Cu O C H C O O minus Na plus. Clear? So this is the filling solution. This is the result of the filling solution that we get. So we have two filling solution basically. So one we have CuSO4 and one we have potassium sodium tartrate. So we react both of them to give this thing. Now this is the main species that is involved in reaction. Now what about the Tolvin's reagent? So Tolvin's reagent complex looks like this. It is Ag NH3 all twice plus H2OH minus. We have 2 moles of this. So this is the complex that we treat our reducing sugar with. So we treat both of them. Then we will get our carboxylate ion plus Ag. Okay, so carboxylate ion plus Ag. Now in each of these reactions, our species that we are taking is being reduced to carboxylate. So in each of these we are getting carboxylate. So this is the reaction involving this. Okay, so this is a reaction involving Tolvin's reagent. Clear? Now what are the products that we will get? We will get Ag. We will get Ag plus we will get NH3 also. Ammonia, H2 and your carboxylate ion. So carboxylic acid ion will look like this. So whatever may be the group, wherever the CHO was present or the free OH group was present, you will get it as this RCO minus. Clear? So this was about reducing and non-reducing sugar. So why I have mentioned it more, because when you will see the structure, the Howard projection, you will find that we find it difficult to identify that it is sugar and it is non-reducing sugar. If you know the name and the names are given, then good enough. If names are not given, the structure is given, then in that case you will find difficulty, and for that you have to see the first position of the structure. It is the first position, that is a different case to discuss. We will see when we will talk about the Howard projection. Now we will try to read about or get a detailed explanation about each of the type of saccharides, mono, di, tri. We will try to get an idea about each of these. So we will start with the monosaccharide. So what was monosaccharide? If you remember, so monosaccharide was a carbohydrate, then cannot be reduced further. Okay, sorry, they cannot be hydrolyzed further to give simpler units of polyhydroxyaldehyde or ketone. So they are termed as monosaccharide unit. Clear? Now this hydrolyzed only once to break down into simpler units of polyhydroxyketone, but this cannot be hydrolyzed any further. So if I talk about the classification in case of monosaccharide, then we have 2 types of classification. What are the 2 types of classification? The first is your aldose and the second is your two types of classification that are based on the location of CO group, first one, and second one that is based upon the number of carbon atoms in the chain. So on the basis of location of CO group, we can have two types. So if the CO group is present as a first position, okay, if the CO group is present at the first position, we call it as aldose. But if it is present at the second position, we call it as ketones. It will be ketose, sorry. Ketone. Now, how you will identify the first and second position? So for that, you must know about this Fisher projection and how it is written. So there are some rules regarding it. Okay. So first of all, you have to put all the carbon chain in one line. Okay. Now, the most oxidized form of the carbon is generally placed upside. Okay. And if it is not placed on the uppermost side, then it should be placed such that the most oxidized form comes earliest. Okay, it can come earliest. So you can see the two structure. Now, if I have drawn the structure like this, if I would draw the structure like this, CH2, OH, CHOH, again CHOH, one more CHOH, then we have CHO. Now, if you look at both of this structure, I'm not talking about the spatial arrangement. If you just see both of these structure, you will find that the linkage is same in both of this. Okay, linkage is same in both of this since we have rotated in plane. So we do not have any difficulty with this molecule change. It would be like this rather than this. Yeah. Clear? So it is the same molecule. We have just rotated in plane by 180 degree. So let me make a rule here that if you see a Fisher projection, okay, so this Fisher projection looks like this. First of all, we have 3C and 1 CH2. We have H on this side and OH on this side. Now, if I rotate 180 degree in plane rotation, so what I'm doing, I'm just rotating this either clockwise and anti-clockwise, it does not matter. You have just to rotate it 180 degree. So this H will go at the bottom, this carbon will go at the bottom, and this will go up. So then it will look like CH2, OH, OH. I'm not mentioning the carbon, it is understood. Now both of this structure are same. There is no difference in them. Or the molecules are also same. But there are some you can say sign conventions that are used for writing the Fisher projection. Now if you see here in this structure, the most oxidized form comes at the first position. If you go from up to down, while if you go up to down in this one, okay, then you will find that the most oxidized position is at 1, 2, 3, 4, 5, fifth position. So this is not right. This is not the right way of writing the Fisher projection. For that, you have to write in such a way that the most oxidized form comes at the first. The most oxidized form, why? Because it has less number of hydrogen as compared to any other carbon. So it is the most oxidized form. Clear? Similarly, we can have ketose. Okay, so you cannot write ketose again in this way. So if you write it in this way, CH2, OH, we have OH, H, again one more OH, H, and we have HOH. What we have done, we have rotated it. We have CO, we have CH2OH. Now again, we have done a 180 degree in plane rotation. So in plane rotation means we are rotating in the plane. You cannot rotate this Fisher projection out of the plane. Means you cannot, if you have a say this is a structure like this, you cannot rotate it like this. You can rotate it on the plane in this fashion. Okay, clear? Similarly, here also we have rotated it is in the plane, like in this fashion. Now since we are rotating it, this one will go here, again this one will go here. So we have done the same thing, and this at the bottom will come at the topmost. Now okay, the molecule is same, we have not changed anything, but the difficulty with this is it is not the right way of writing the Fisher projection, because again if you try to number it from top to bottom, similarly this one, yeah, okay. So in this case we have our most oxidized form, which has the least number of hydrogen, is placed at the second position. But if you talk about this, we have it at the fifth position. So this is wrong. This way of writing is wrong. You can do your internal problems using this, but you cannot write the final structure in this form. Clear? So this was about the classification of monosaccharide that is based upon the position of CO group. So here CO group at the second position, here the CO group at the first position. We have aldose and we have ketose. So this is ketose. It is not ketone, it is ketose. Next classification will be on the basis of the number of atoms in the chain. Now student, you will see that the structure that are being used here, or the name that are being used here, will change when we will go to more deeper into chapter. And you need to remember the name of those, because sometimes questions are asked directly using the name, and if you are unaware about the names, then you will find it difficult to visualize it. Clear? Right. So let us start this classification. So this classification looks simple. So first of all, how we are writing the name of this compound. Why are we writing O's here? Triose, ketose. So we will see the reason for this when we will study about the cyclic structure. Okay, when we study about the cyclic structure, then you will see why this O's, from where does this O's came from. So tri means 3 carbons. 3 carbons are there, 1, 2, 3. Now do not make the mistake of not counting the carbon that is being attached with double bonded oxygen. Okay, so do not make this mistake. Students always make this mistake that they do not count the number of carbon along with this carbon that is attached to oxygen, doubly bonded to oxygen, I would say. Yeah, so how many carbons it has? It has 1, 2, 3 carbons. So therefore it will be termed as triose. Again we have tetrose. So it has 1, 2, 3, 4 carbons. So it is tetrose. Then next one is pentose, which has 1, 2, 3, 4, 5. 5 carbons. So it is pentose. Next one is hexose, which has 6 carbons. It is 1, 2, 3, 4, 5, 6. Now talking about the common name, so we will see a trick for that, how to remember the common name. For now, just remember it as pentose, hexose, triose and tetrose. So if I talk about the previous structures that we have seen, so if you talk about the glucose, so glucose is a hexose and an aldose. Okay, so you try to just when we will talk about more about this different type of carbohydrate, just try to say divide those names along aldose and ketose plus this triose or tetrose, pentose, hexose. Okay, just try to classify them. Now this was the classification based on 2 different types of the monosaccharides. So far what we have studied, so we have started from carbohydrate. We have said that What are carbohydrates? So carbohydrates are hydrates of carbon. So it is a primitive definition that will be demolished when we study some exception examples. Okay. Then what we did is we have a general definition. So the general definition says that aldehyde, or sorry, a carbohydrate is a polyhydroxy aldehyde or ketone that is optically active, and on hydrolysis of that we get simpler polyhydroxy aldehyde or ketone. We cannot hydrolyze them or in some cases, but still it is a characteristics of this carbohydrate. Some of them get hydrolyzed, some of them do not get characterized. Second criteria was sugar, so and non-sugar based on the taste. So if it is sweet in taste, then it is sugar. The example is glucose, fructose. And if it's not sweet in taste, it is called as non-sugar, and the example was starch. After that, we have seen on the basis of reducing nature. So if it can reduce Benedict's reagent, filling solution, Tolvin solution, then it is called as reducing sugar. And if it cannot do so, it is called as non-reducing sugar. The common example of non-reducing sugar were sucrose and your raffinose. So for say quantifying them, or dividing them into reducing or non-reducing sugar, the general trick was that you find a free CHO group in that given structure, else you find out a free OH group that is present at the first position of the Howard's projection. So we'll see what Howard's projection is, as I have told you earlier. So if you talk about the different Benedict solution or filling solution, Tolvin solution, they all three have a different type of reagents, and they all three give the same structure of the carbohydrate. So if we talk about Benedict's reagent, so the main oxidizing agent, the main reducing agent that is getting reduced is the copper 2+ ion, and the species it is forming is copper oxide, and copper oxide that is having brown color, while our solution was copper sulfate in alkaline citrate solution. Clear? And our aldehyde or free OH group is being reduced to carboxylate ion. Okay, clear? Then we have the filling solution. So filling solution A and filling solution B, two type of filling solution you have to take. First one was copper sulfate, and second one was our potassium tartrate. So we will react both of them, then you will get sodium potassium tartrate, which have the structure that we have seen earlier. So we have tartrate, and one counter ion is potassium, and another counter ion is sodium. So if you treat your filling solution A and filling solution B, if you add both of them and treat it with your reducing sugar, then it will reduce your copper 2+, again your copper 2+ to copper plus. Here also the species that is getting reduced is same, and it is again converted to copper oxide that is having red brown purity. In this case also, your free aldehyde or your free OH group at the first position is oxidized to carboxylate ion. Next, we have the filling solution. Okay, we have the Tolvin solution, Tolvin stance, in which we use a complex of silver, which is made upon by treating our ammonia with silver. In that reaction, what we do is we treat our Tolvin's reagent with our aldehyde or free OH group of the first position of the Howard's projection, and then we get carboxylate ion plus we get a complex of ammonia, which we have seen just now. And the end point means the indicating end point is the formation of silver color. So this were the three classifications. After that, we have started to discuss each of these separately, starting from the monosaccharides. So what was monosaccharides? So monosaccharide were those which do not get hydrolyzed further. Okay, so they do not get hydrolyzed further into simpler units. And the most common example is glucose. And we have done two types of classification of the same. So what were the classification? First was the position of your C double bond O group. So if your C double bond O group is present at the earliest position, and then at the first position. So first you have to convert your Fischer projection properly, orient your Fischer projection properly, so that the most oxidized form comes quicker when we go from top to bottom. Then if you do so, after that, if your CO group, the carbonyl group, is present at the first position, then we would say that it is aldose. If it is present at the second position, we will call it as ketose. So this was the first basis of classification. What was the second basis? The second basis was based on the number of carbon atom. So if it has one carbon atom, then we call it as triose. If it has more than 3, suppose 4 carbon atoms, then we call it as tetrose. If it has 5 carbon atoms, then it is called it as pentose. And the last with the 6th one is called as hexose. Now one more important point, that this triose, tetrose, pentose, hexose can be aldose and ketose both. So you will see a variety of aldose and ketose. So if I talk about the triose, we can have raffinose. Okay, we can have raffinose. Sorry, not raffinose. I would say get Raxel, all arteries gladly make get Raxel. Okay, so we have the example of triose as pentose as raffinose. Okay, this one will be glyceraldehyde. Glyceraldehyde is an example of aldose plus triose. Here, then we have tetrose. So tetrose is basically raffinose. Sorry, GET. Erythriose. Erythriose. This is an example of pentose and an aldose. Then we have hexose. The very common example will be glucose, having 6 carbons. Okay. Now, what about the example of fructose? What about the example of ketose? So ketose includes fructose. So fructose is the most common example. So basically, fructose is having a chain length of 6, and it is a ketose. So all the example are aldose, and fructose is ketose because it has a CO group. Done. Now, this was all about today's class. Now, in the next class, we will try to study this monosaccharides example one by one. We will start with glucose. That is, I think, the most important one. We'll study various properties of that. So what we will study tomorrow is that we'll mainly study about glucose and about its structure, physical properties, and your reaction. Now, I would suggest you just go through the Fisher projection one more time. What is Fisher projection and how it can be formed? Okay, so the Fisher projection looks like this. Okay, this is the Fisher projection. This is called as the Fisher projection. Now, if I talk about the stereochemistry, suppose we talk about the stereochemistry of this thing. So by this we mean that our groups that are present on the say this one, sorry, horizontal bars are present down the group. Okay, and this CHO group will be present upside. Similarly, this CO will also have this H here on the dash, that is a down one, and this OH also on the down one. Similarly, this C also. And at last, this CH2OH is present upside. So this is the transformation of this into your dash and wedge form. So I should suggest you that I would suggest you that you should learn more about the Fisher projection and how you can convert your normal structure. So suppose this is the normal structure. Okay, So if you have studied about the stereochemistry, then you must have seen this kind of structure. Okay. Now this is different and Fischer projection is different. So you should be aware about how to convert this normal aliphatic chain into your Fischer projection. When you got the dash page, how you will convert it into Fischer projection. You will use this thing later on to study the glucose. So that was all for today's class. So I would suggest you just study a little about glucose, about its structure and say properties, physical properties and reactions. That would be beneficial for you. So with this, I end my lecture. Thank you.